started. So, today we're going to start in on probability. So we've already talked about probability a little bit earlier in the semester. And what we did was we had an experiment where we flipped a coin 50 times and recorded the results. And at the same time, we had somebody just kind of pretend to flip a coin and just make up results. Okay? So the point of that experiment was to show what we think randomness looks like versus what it actually looks like. And so we had results for our coin flip that were, we had a bunch of heads in a row or a bunch of tails in a row, but on the made up version, it was pretty evenly distributed. There wasn't a whole lot of those big groups of heads and tails. Okay? And again, it's because probability does not look like what we usually think it looks like. So let's go ahead and take a deeper look at probability today. So I've got some dice for us to look at today. So if I were to roll this dice, there's a certain probability for each of the numbers on these faces to come up when I roll it. For instance, 3. How many 3s are on this die? There's only one of them, yeah. So if I roll this die, there's only one possible way that I can get a 3. And that's if it lands on this particular face. So we would call that a favorable outcome. And on this die, there is one favorable outcome for a 3. Okay, well, how many numbers are there total on this die? 6. So we would say that the number of things that we want to happen is 1, but the total number of things that can happen is 6. So we would say that there is a 1 in 6 chance of getting a 3. Okay, this is very simple probability. In fact, this is very similar to what we were doing on the exam with that problem that said, the phone company has a certain amount of complaints each month and it gives us a table, and we had to look at one of the categories on that table and find the percent. Well, it's taking it out of frequencies, and this is kind of the same thing as that. We're taking a part or a particular category and comparing it to all the rest. So we can actually get a percent out of this as well. If we have a 1 in 6 chance of rolling a 3, then we just divide 1 by 6 and then multiply by 100, and we get a percent chance. So the percent chance of rolling a 3 on this die is 16.7. And so about a 17% chance. So what this says is that if I roll this thing 6 times, only about one of them is going to be a 3. Now, I'm rolling this thing a bunch. I've definitely rolled it more than 6 times already. I still haven't gotten a 3. So where's my 3? Well, this tells us basically what we can expect, but it isn't a guarantee. I can roll this thing 6 times. I can roll it 100 times. I can roll it 1,000 times, or even 1,000,000 times, and I'm never guaranteed to get that 3. That was kind of on the money, huh? Okay? So I'm never guaranteed to get that outcome that I want, but as we roll this thing more and more times, it's going to tend to go towards this. So if I roll it 6 times, 1 out of those times might be a 3. If I roll it 100 times, if I roll it 600 times, about 100 of them will be a 3. If I roll it 6,000 times, about 1,000 of them will be a 3. Now, all of these, if we were to divide them, so 100 divided by 600, that's still the same percent. 1,000 divided by 6,000, that's still the same percent. So this percent is telling us what we can expect our results to look like, again, over time. So it doesn't matter how many times we roll it, it's always going to have this percent chance. It's always going to have this probability of rolling a 3. Again, that doesn't mean we're guaranteed to get a 3. It just means that the chance of getting it is going to be about 17%. Now, as we roll it more and more and more and more and record the results, it's going to look like this. About 1 in every 6 of those results is going to be probably a 3. Okay? Any questions? None? Okay, let's look at some more examples of this then. So let's say instead of just looking for a 3, I'm looking for any number above 3. Or let's say 3 or above. So I can roll a 3, or I can roll a 4, or I can roll a 5, or I can roll a 6. Okay, so what's the probability of rolling a 3 or higher? Well, again, what we need to look at is how many favorable outcomes do we have? How many outcomes do we have that match what we want? Okay, so we can have a 3, a 4, a 5, or a 6. That's 4 favorable outcomes on this die. And again, how many possible outcomes are on this die? 6 of them. There's 6 faces. So it's 4 and 6 chance. Now, really we ought to reduce that. This is a fraction. This can be reduced. What can both of these numbers be divided by? By what? 2, yeah. So if we divide both of them by 2, we get 2 out of 3. And as a percent, 2 out of 3 should be 66, yeah. So this would be a 66.7% chance. So I could roll this. Let's see. I'm going to roll it, say, 6 times. So that means that about 4 of them should be what we want. So we got a favorable. No. No. Yeah. No. And yes. I mean, actually, that fits. Okay? Again, is it guaranteed to fit every single time? No. Probability only says what is possible and what is likely, not what is going to happen. It is not an exact prediction. Okay? That's because randomness cannot be predicted. We know what randomness kind of looks like. That's what these probabilities say. But we will never know exactly what every single outcome is going to be every single time. Does that make sense? Any questions? None? Okay. Then let's make this a little bit more interesting. Let's add another die. So I got my normal 6-sided, and then I've got this guy here, an 8-sided die. Okay, so again, this one's 6 and this one's 8. Okay. So now, instead of just rolling 1, I want to roll 2 die. And let's say I want to get a 5 on this one and a 7 on this one. Okay, so when I roll this, I want to get a 5 and a 7. What's the probability? Well, we know the probability for each of these separately, right? What's the probability of getting a 5 on this die? It's a what? 1 out of 6, yeah. There's 1 5 on this, and there's 6 possibilities. Okay, what's the probability of rolling a 7 on this die? Keep in mind there's 8 numbers on this die. It's a what? 1 out of 8? Okay. So the probability of rolling a 5 on this one is 1 out of 6. The probability of rolling a 7 out of this one is a 1 out of 8. So how do we put these two together? Well, we've got to understand how rolls work. Okay, so let's keep this in the back of our mind real quick. So again, on this die, there's 6 different possibilities. Okay, we can roll a 1, a 2, a 3, a 4, a 5, or a 6. This one, there's 8 possibilities. So there's a 1, 2, 3, 4, 5, 6, 7, 8. Okay, so let's say I roll this die and I get a 6. And then I roll this die. What numbers could pair up with this 6? If I roll this one and get a 6, what is possible to roll on this one? Well, I could roll a 1, or I could roll a 2, or I could roll a 3, or I could roll a 4, or I could roll a 5, or I could roll a 6, or I could roll a 7, or I could roll an 8. There's 8 possibilities after I roll a 6 on here. Now if I change the number, does that mean I have different possibilities over here? No. I've just changed this one. This one hasn't changed at all. So for 2, I could still roll a 1, 2, 3, 4, 5, 6, 7, or an 8. So there's 8 possible matches for this one. In fact, for all of these numbers, there's 8 possible matches. So how many possibilities are there total? Well, we have 1, 2, 3, 4, 5, 6, 8. So in other words, what we're doing here is we're taking the possibilities here and multiplying them by the possibilities here. So 6 times 8 is 48. There are 48 possible outcomes if I roll these 2 die. Okay? And it's the same with these probabilities. Again, I wanted to see if I could roll a 5 and a 7. The probability for each of these was a 1 out of 6 and a 1 out of 8. We multiply them, just like we multiplied these. 1 times 1 is 1. 6 times 8 is 48. There's one possible way that I can get 5 and 7. And there's 48 possibilities, so it's a 1 in 48 chance. Does that make sense? Okay, so if we have more than one thing going on, we need to multiply those probabilities. So maybe I have die like this. These are called percentile die. Okay, so like if I roll this would be 62%. Okay? So I want to know the possibility or the probability of rolling a, well, I don't know, 36%. Well, didn't get it there. But what would that probability be? Okay? So again, I want to get 32%. So I need to get a 30 on this die. Where is that? There's 30. And I need to get a 2 on this die. Well, what is the probability of rolling a 30 on this die? There's 10 sides. 1 out of 10. And what's the probability of rolling a 2 on this die? Well, it's still 10. Yeah, so it's still also 1 out of 10. So multiply that. 1 times 1 is 1. 10 times 10 is 100. Good. So it's a 1 out of 100 chance, which makes sense. I mean, if I'm rolling percents, percents are always out of what? 100. Okay? So if I wanted to roll a 32, I have a 1 in 100 chance of rolling that. Any questions? Make sense? Okay. Let's do something slightly different. I meant to bring a deck of cards today, but I forgot, so I apologize for that. Well, let's just pretend that we're drawing cards. Okay? So, how many cards are in a standard deck? 52, yeah. So, in a standard deck, there are 52 cards. Now, what I want to try to do is I want to try to pull a club out of that deck. So how many clubs are in a deck? Not just the face cards, but also the number cards, clubs. We have, let's see, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, and Ace, right? So that's 13. So if I want to pull a club out of this deck at random, I have a 13 in 52 chance to do that. What is that as a percent? Let's see. 13 out of 52, well, duh, it's a quarter chance. There's 4 suits in a deck, so if I want to pull a card from one of those suits, it's a 25% chance. Okay. Now what if I want to do it again? I've already pulled that card out, so it's gone. I want to go back into that deck and pull another card. So what's the chance of pulling another club? Not out of 52. 12 out of 51, because again, we've lost a card. But good, 12 out of 51. Because I've taken a club out, now I want to see what the chance of getting another one is. Well, there's only 12 clubs left, and there's only 51 cards left in the deck. Okay, well again, we need to multiply this to see what our total probability is. So 13 times 12, oops, 13 times 12 is 156. Over, let's see, 52 times 51 is 2,652. So my chances are getting a little bit slim there. Let's see, what percent is that? 156 divided by 2,652. Oof, that is a like 5.9% chance. About a 6% chance. Okay, well, I want to do it again. So maybe I got lucky both 2 times. I want to try again. What is my new probability that I need to multiply this by? 11 out of 50. Again, I pulled a club. That means we have 1 less card. So let's see what we get. So 156 times 11 is 1,716. And then 50 times 2,650, oh, 652, sorry, is 13, oh, I'm sorry, no, that's 132,600. What's that as a percent? Let's see, 1,716 divided by 132,600 is a tiny percent chance. Let's see, that's a 1.3% chance. So as I keep pulling cards, I have a less and less likely chance to pull another club. Okay? Essentially what this looks like as a series is I start out with 13 out of 52, and then 12 out of 51, then 11 out of 50, 10 out of 49, and so on and so forth, just like that, until we get to, I believe it's 1 out of 39, let me check, 52 minus 13, hold on. Yeah, it's a 1 in 40, sorry. Okay? So this series goes on and on and on until I only have one card left. And I want you to notice something about this series. As we multiply more and more of these probabilities together, we're going 13 to 12 to 11 to 10 to 9 to 8 to 7, so on and so forth. Same thing with the 52, 52 to 51 to 50 to 49 to keep going, okay? This is what we call a factorial. So a factorial, so for instance, like the top here, this would be 13 factorial. Say 13 with an exclamation point next to it. So this represents 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10 times 11 times 12 times 13. Okay? In fact, let's see what that is. 13 factorial. Luckily the calculator has a factorial button. Is huge. Let's see, that's 100,000 million. 6,222,000. I'm sorry, 222 million. 20,800. And then it'd be out of whatever this is. And I'm not going to calculate that. We don't need it. Okay, but you can see that these things increase very quickly. So as we keep pulling more and more cards out of there, the chance of getting another club is getting less and less and less, and it's quickly becoming almost zero. Okay? Now these factorial things are actually quite powerful. Let's take a look at that. Any questions though? Okay. So one place you see them is in security. Okay? Think about high school. Everybody had a locker in high school, right? And that locker has a dial on it to put a code in with. That actually has a certain amount of combinations, possible combinations, so possible codes that you could put in, based on factorials. So think about your locker back in high school. How many numbers were on that dial? 60? Yeah? Okay. So the dial had 60 numbers on it. And how many numbers were in the code that you put into it? 3? Okay. Okay. Now, if we want to know the total number of possible codes that you could put into this lock, that would kind of tell us how hard it would be to get into it, just by kind of guessing. Okay? Of course, what I'm saying here is that there is one code, one favorable outcome out of all of the total outcomes. So we need to know what the total outcomes are. How do we find that? Well, what we do is we have to do something called a permutation. Okay? So a permutation is a way of organizing possibilities into slots. Okay? So for our code, there are 60 possible numbers that we can put into our code, right? And there are 3 ways, or there's 3 slots to put them into. So this permutation is going to take this and calculate how many ways we can do that. So how many ways we can put 60 numbers into 3 positions. Okay? So again, permutation. Now the thing to note about this is that order matters. Because of course a combination of 1, 2, 3 is not the same combination as 3, 2, 1. If your locker combo is 1, 2, 3, you don't want somebody to be able to come up and put in 3, 2, 1 and get in. Because that means that there's more than one code to that locker. So again, in a permutation, order matters. Okay, so here's how it works. We have a formula called NPR, where P is just the name of this formula, and N and R are the numbers we're going to plug into it. And we have N factorial over N minus R factorial. N is the number of things that we're trying to organize. So N is the number of things on that dial. So we have 60 numbers on that dial. This is our N. Okay? R is the slots that they can be organized into. So we have 3 slots in our code. That's our R. So let's go ahead and plug these in and see what it looks like. So again, N is 60. P is just a name, permutation. R is 3. So we have 60 factorial over 60 minus 3 factorial. Okay, so now we need to follow our order of operations to solve this thing. Well, first things first, we need to do 60 minus 3. So 60 minus 3 is 57. So now we have 60 factorial over 57 factorial. And, well, now we'd have to do 1 times 2 times 3 times 4 times 5 times 6 all the way up to 60, and then do that again for 57. That seems kind of hard. Let's find a shortcut. And in fact, there's quite a nice shortcut for this. Again, remember that this is 1 times 2 times 3 times 4, all the way up to 60, right? And then 57 is pretty similar. It's 1 times 2 times 3 times 4, all the way up to 57. Well, since these are multiplying numbers, and they're being divided by the same multiplying numbers, they cancel. We have 1 divided by 1, it's 1. 2 divided by 2, it's still 1. It's canceling. All of these are canceling. In fact, any numbers that are the same between the top and bottom will cancel. So this is going to cancel all of these numbers all the way up to 57. So even 57 is going to get canceled, meaning there's only a few numbers left on the top. And those numbers are 58, 59, and 60. So actually, we only have to multiply those three numbers to get our answer. Does that make sense? How I'm doing this? Yeah? Any questions? All right, so let's go ahead and see what this is. 58 times 59 times 60. For your high school locker, there were 205,320 different codes. So if somebody were to walk up to your locker and randomly put in a code, they would have a 1 in 205,320 chance. Well, let's see what that is as a percent. Oof. Pretty tiny. Let's see. That is 0.123456. A fraction of 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 a percent. Tiny, tiny, tiny probability that they'd be able to put in the right code. Now, of course, they can keep putting in codes, and as they keep putting in codes, they're going to be more and more likely to get the right one. But putting it in that first time, oof, not a great chance. However, interestingly enough, this is actually not that great. Your locker in high school really wasn't designed to be the most secure thing in the world. It's really just designed so that the normal student walking down the hallway can't just put in any number and get into your locker. However, if somebody really wanted to get in and they were skilled enough, this wouldn't take them very long to crack. Maybe a couple hours. Okay? So how do we increase the security on this locker then? Well, we could give ourselves more numbers to choose from. Maybe instead of 60 numbers on the dial, we have 100 numbers on the dial, right? Well, we could also increase the size of the code. Or we could do both. But which one is more useful? Let's find out. Okay. So let's compare some things here. First, we know that the one that we just calculated, 60P3, is a 205,320 codes. So that's how many codes that one has. Let's increase this to 600, so multiply it by 10. Okay? So that's going to give us a whole lot of stuff to choose from. Let's see what we get from that. So luckily, the calculator has NPR in it, so we just got to plug in our numbers here, 600P3. Okay. So if we increase the size of that dial to 600 different numbers, we get, let's see, 214921200, so that's 100,000 millions. So 214,921,200 different combinations. All right, well that definitely helps. But what if we went the other way? And instead of increasing the size of the dial, we increase the size of our code. So we'll drop this back down to 60, and then make this 30. Okay, so instead of multiplying this by 10, we multiplied this by 10. All right, let's see. So make this back into 60 and this one into 30. Oof. Huge number. Let's see, this is 3.137 times 10 to the 49th power. Now, if you remember back to high school again, maybe your science class, you learned about scientific notation. What this means is that we would move this decimal 49 times to the right and get a number. And I mean, let's see, that'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. I don't think I can fit it on the page, man. This is a huge number. In fact, this is so astronomically huge that it dwarfs what we did before. So increasing the size of the dial, nah, that's not going to be as effective as just adding a few more digits to your combo. Okay? So think about this. When you sign up for a website, they want you to make a password, right? And what are some of the things that they want you to put in your password? They want to make sure you have, letters, both uppercase and lowercase. Maybe some numbers thrown in there, some symbols, things like that. Well, is that increasing the size of the dial, so the things that you can put into your code, or is that increasing the size of the code? It's just increasing the things that you can put into your code. That's just increasing the N. So while that does increase the security, it doesn't increase the security anywhere near as much as if you just made a slightly longer password. The idea behind it is that, well, if you have a whole lot more things you can choose from, then it's harder to crack. No. In fact, password cracking done by computers, a computer does not care if you have a special character or not. It thinks exclamation point is basically the same thing as a letter. Okay? Now, if you have a longer password, then because there are so many different possibilities in that password, it makes it really hard for the computer to guess it. It can guess, digit at a time, but man, if it's got this many different passwords to go through before it finds the right one, it's going to take it years, like decades or millennia to get this done. Okay? So when you see a website asking for you to make a password, yeah, go ahead. Put in some special characters and whatnot. That will increase the security. But just make it a little longer. That'll give you a really secure password. Any questions? None? All right. Then I believe that will do it for today. Friday we will pick up with some more of this stuff. Remember that tomorrow in Ms. Lamar's class you'll be taking your test. Okay? So I hope you have a good one.